can start recording. Okay, welcome back, everybody. We are very pleased to have Sabrina Pasterski. She is a postdoc at Princeton IAS, and she will talk us about celestial amplitudes. So you can start, Sabrina.
Hi, so thank you guys for having me, and I am happy to be talking at this school. So first of all, I welcome any questions, and so if you interrupt me, feel free to interrupt me throughout. I emailed you guys the lecture notes ahead of time, so hopefully you guys have that. For this first lecture, we're going to focus on kind of setting up what celestial amplitudes are, like the motivation for it. So basically, if anybody's following along, we're going to go relatively quickly through sections 1 and 2 and see where we end up at the hour. So okay, so let's start. So what are celestial amplitudes? So basically the thing that we want to get to by the end of, so I guess Friday, is the following. So we have typical S matrix elements in momentum basis, and we want to map them to a set of correlators on the celestial sphere. So there's some dependence on some space-time points and the celestial sphere. So for today, what we want to basically do is understand exactly maybe why this map is even natural from the first place, from the kinematics. Also look at some of the basics that go into the representations that are taking us from the momentum space eigenstates to these conformal correlators, and also motivate what the celestial sphere even is. So the fun thing about our story is the following. So basically, so let's look at the why. So the interesting observation by Strominger et al. Is that basically you have an infinite number of symmetries hidden in the IR. So that's going to be the focus of the next lecture. So the IR tells you that you have infinite dimensional symmetry enhancements. And this is going to be relative to, so instead of the space-time symmetries just being Poincar and like everything that you normally do from there, there's actually, when you include gravity in the bulk, you have a natural extension of Poincar to include infinite dimensional enhancements. And so those are going to be motivated by IR physics coming from soft theorems. So the first kind of stepping stone towards this holographic dictionary is showing that connection, because it motivates looking for a new rearrangement of things. So this is step 1, is that you have these infinite dimensional symmetries. And so if you have a prescription for studying scattering that puts those symmetries first and foremost, you have a better chance of taking advantage of that in the most opportune way for studying constraints on scattering and consistency conditions. And then the second step with that is that basically, so now that you have these extra symmetries, you want to see how they're arranged. So it happens to have this feature that these 4D, what we're going to call asymptotic symmetry, word identities look like they're going to be 2D currents. So basically what's going to happen is that the reason why we have this description in terms of conformal correlators is being told to us from the structure of this asymptotic symmetry enhancements. And so then the third step is basically going to be do the map here, and see where it takes us. Like, hey, what can we learn? Okay, good. Okay, so that's the highlight of like the outline for the goals for today. Being to get some sense of this first step of like why we can even expect to be able to do this map, and then to also get through basically the background we need to set up this IR story. So that's going to be understanding the causal structure of Minkowski spacetime, so the Penrose diagram for that, what future and past null infinity are, et cetera, because that's going to be basically the arena that we're looking at, where we're thinking of scattering in terms of a spacetime perspective, so that we can map asymptotic symmetry stories to S matrix behavior. Okay, so that's roughly a bit of a motivation through section 1 in the notes. And so the next thing that I just want to highlight, and so see if I can get rid of my poor drawing errors. Okay, so the next thing that we want to highlight, so this is the motivation, is that like kinematically, we can do this. Okay, so basically the statement is just that Lorentz transformations in 4D is going to be isomorphic to 2D conformal transformations. So in practice, if we take the light cone of R 1, 3, and we embed a null vector Q mu is 1 plus W, W bar, W plus W bar. So I'm using basically W's in C. So given that embedding, basically what I have then is I can do Lorentz transformations in this embedding space, and that will mount to doing conformal transformations on these W coordinates. So essentially what's going to happen is that X mu is going to map to MW nu, X nu, while W will undergo a Mobius transformation. And so, okay, so let's maybe, I guess, unpack where we've seen this before. So a lot of times when we're talking about building up spinor variables, so whether it's spinor helicity variables or the spinors that were like basically the representations when you're looking at the field content in setting up different like A mu, H mu nu, or spinor fields, you're going to often use the following isomorphism. So if I have my Pauli matrices sigma I can construct the following combinations: sigma mu, AB dot is identity sigma I, and similarly with sigma bar, negative sigma. And then with these guys, I can go from a vector to a force to a two-spinor matrix. So basically, VAB dot is going to be V mu, sigma mu, AB dot, and then similarly V mu, I can get back with the trace. Okay. Okay. So basically, what I want to point out here is if I then take and value a matrix that's in SL2C. So basically now I have the requirement, sorry, this is C. Let's see. A minus BC is equal to 1. Then basically I would find that M dagger X mu sigma mu M is a Lorentz transformation. So it intertwines me between the two representations. And so for the purposes of what we care about here is that basically, like all I want right now is that I have Lorentz transformations in 4D, mapping me naturally to what will be conformal transformations in the celestial sphere. And when I do that, then basically I can kind of force myself into using similar intertwiners for representations of like the definite momentum states and take me to Boost eigenstates. So I'll show you how to do that next. So basically what's happening right now is we're just showing that the groups are the same. I think this is relatively familiar. But the point I want to mention now is that basically, like if we just took the point of view of, okay, so like you have 4D, like Poincar transformations, the Lorentz transformations are isomorphic to the global 2D conformal transformations. In 2D, normally we would have local conformal transformations. So if I just wanted to say that I have my metric GAB is, so in this case, let me just look at the 2D metric. So if I started with ds squared is dw bar, and I demand that under some transformation, I basically map dw bar, then basically this factor it can gives me more freedom than if I just was good. Okay, so the place we're at right now is that we have basically Lorentz in 4D. 4D is conformal in 2D. Kinematics then will let us go from a P mu eigenbasis to a to celestial primaries. And what we first task is to basically understand like what is the celestial sphere. So one theme, so basically in the first, like section 2 of the notes where there's a lot of just random things about quantum field theory put there, the point was to set up conventions so that I can go from momentum space to repeating everything in my celestial basis later. So for me, really section 2.3 is the important part, which is the celestial sphere. But I do want to point out that basically, typically when we'd be looking at scattering, we'd have some on-shell particles. So when we're massless, we have a light cone in p mu. And if we're massive, we would have a hyperboloid. And so when I want to talk about the celestial sphere, I'm talking about looking at the night sky and seeing the stars coming at me. So what I'm going to say is what that will be, that's going to be past null infinity, but like, let's save those words for later. If I have a massless particle, then I am going to basically be parameterizing its formal momentum, right, with a reference direction q mu and some energy scale omega. So I already naturally have a celestial sphere for the direction in which my momentum is heading, and I'll make that more precise in a minute. For a massive particle, we basically need to pick a point and then boost towards it, and then the states that you create are essentially some sort of integral kernel that's going to force the covariance property so that it's an eigenstate under boost in a given direction. So I'm boosting towards the North Pole. Okay, towards like North Pole. Maybe North Star. Good. So what I want to do is I want to talk about the celestial sphere from that point of view. So basically what's going to happen is the essence of this story is that there's some sort of omega goes to 0 limit in momentum space that's supposed to equal some asymptotic symmetry. So these asymptotic symmetries, by what I mean asymptotic, is that like they're actually how the space-time behaves at large R, so large R. So what's happening with the story is the following. Basically, I want to be able to understand how going to soft limits would correspond to going to large R. And in principle, it kind of like long distance scales being related to low energies is consistent with like our intuition for doing a Fourier transform. So that won't be a problem. But in the meantime of kind of codifying that, we're going to see essentially how the single particle states that I would prepare on a Cauchy slice that is given, say, fixed time, are going to then, when I change that Cauchy slice and push it to the conformal boundary, give me these correlators on the conformal boundary. So when I say celestial sphere, what I really mean is I have a Penrose diagram for Minkowski space, and I am looking at this sphere that is the different directions of geodesics that can come to me from like geodesics. So let's go through this diagram and actually work it out. So what I have is I have my space-time coordinate x mu, and this is in section 2.3 right now, the notes if anybody is following along. And I have stereographic coordinates for my celestial sphere. Basically right now I'm just literally changing to radial coordinates. And this z is going to be e to the I phi tan of theta over 2. So I've taken a point in the night sky, I've doubled it. So this would be z equals 0, say, and this is z goes to infinity. And then what I have is I have basically t is equal to, u is equal to t minus r here. So t is equals r. And then I have a retard, so that's a retarded time, and then I have advanced time here where v is t minus r. So what's going to happen, so what I'm basically doing is I am choosing coordinates that are going to be appropriate for massless geodesics that are going to be approaching this future boundary. So basically what I'm doing right now is I start from these coordinates here, and I'm still just in Minkowski space for the moment. And the point is going to be that when I look at spacetimes that are not actually Minkowski space, but approach it in some codified way that I'll codify, we end up getting metrics that are basically almost flat, and in that sense we'll have the like symmetries or enhancements of symmetries that we would expect for a flat background. So let's look at these coordinates. So basically I have u is t minus r, v is t plus r. And now what I'm going to do is I'm going to take these coordinates and I'm going to rescale them. So I define a coordinate capital U as follows, and then capital V as follows. And when I do that, basically what I'm going to do is, effectively all I'm doing is basically saying that I have a finite coordinate range. So from -pi/2 to pi/2 for each of these big U's and V's. And so that's why I can literally draw it on a diagram. So on my iPad, I'm drawing this bad looking diamond, and that diamond is supposed to be all of space-time. And now, of course, you can always just change coordinates to kind of do that. But the point is that what we're going to find is we want to look at what the metric looks like in these coordinates. And then all we care about is the causal structure. So we're going to strip off any conformal factor there. So we do that, and then we do another change of coordinates, U plus V, and R is equal to V minus U. And what we find then is if we then look at our metrics, so we started with ds squared is just negative dt squared plus dx squared. And so one can look at what that is in these U and R coordinates later. I'll write it down later. But what it turns into now in terms of these redefinitions here is the following. So I have some conformal factor, and then I have a negative dt squared plus dr squared plus 2 sine squared r gamma z bar dz bar. Okay, so what all I emphasize right now is that basically I have taken Minkowski space, I have done a change of coordinates so that everything is in a finite patch, and then I've shown that for those finite range of coordinates, I am basically capturing all of Minkowski space, and the metric on it has this conformal factor I can strip out. I can identify this as essentially a patch of the cylinder here, where basically it's wrapping around. It's a little bit hard to draw, but you can imagine this diamond is wrapping a cylinder, so they meet up at the point. Bad drawing. And so what I want to have here is that I have now the structure of these null boundaries. So maybe what I wouldn't have anticipated before is, okay, so typically what we're used to is we have some equal time slice, and then we want to Fourier decompose our fields on it. So I would have basically my mode operator A is some integral of some creation ionization operator, say. I'm going to be schematic with the phase right now, I'll write it down more carefully later. So I would normally be looking at a, say, a t=0 slice, Fourier decomposing my field operator, and then thinking of the single particle states I'm building there. And when I want to create my in-state, say, I would take this time to negative infinity. So the fun thing about this conformal classification is, well, okay, so if we look at this Penrose diagram, I have spatial infinity here, I have past time like infinity here, future time like infinity here, and then I have past null infinity, sorry, minus, and sorry, plus. And the point that I'm emphasizing here is that basically there's different notions of infinity when you're massless versus massive. So if I wanted to just go back and I was a massive trajectory and I wanted to track back where I was coming from, if I never, I guess, came into being, so I've always existed, then I would go back to this point that's past time like infinity. But if I look at where the source of radiation is coming from, basically, if I had a free plane wave going through, it would come in at past null infinity and exit out through future null infinity. So if I think of myself as basically trying to look at the data for the radiative fields in my spacetime, I want to be looking at the data along here. So I want my Cauchy slice to be basically pushed up to this boundary. And so then the interesting thing about that basically is that I want to think of how I would prepare states on this boundary. So let's go about doing that. So the first thing that we want to start with is actually like the appropriate version of this mode expansion here. So I'll look at the, I guess graviton case is easy enough to do first. Okay, so all the factors should be in the notes, so hopefully forgive that. I have right now, okay, so I have my metric G mu nu is equal to eta mu nu plus some perturbation. And what I'm going to do now is basically look at what the free mode expansion would be for my operator. So I have this guy, some polarizations, okay, divide cubed, number 2k0, long mu nu alpha star, well, a alpha, vik dot x plus hc. So I have, of course, also the creation annihilation operators here. So basically, this guy is just my standard. I can think of it as an interaction picture, but basically I've just Fourier transformed and let the them evolve with the energy of the free particle. So right now I'm just thinking this is the free modes. And what I have now, essentially what I'm just saying is that, okay, fine, we've like decomposed it into Fourier modes. And these guys we know acting on like the vacuum. So in this case, the out vacuum would create the single particle state. So now what I want to do is I want to take advantage of the fact that for massless fields, I want to look at future null infinity, which means I want to hold, take R to infinity, holding U fixed. U fixed. So that's going to do something funny here with this phase. So when I have basically e to the I omega q dot x, this guy here is going to look like a rapidly oscillating phase in that large R limit. So what I get, basically remember that T is equal to U plus R. And so then also Q hat dot X hat, sorry, dot X is going to have as R term. So I have basically in my phase, I have an e to the I omega R, and then Q0 here because by the way that I choose the variables, 1 minus cosine theta. So that's contained in here. And so basically the interesting statement about it is that if I'm holding, so then this is multiplied by e to the negative I omega U. So this is the part that's capturing the energy. But when I take the large R limit, I'm essentially localizing myself to theta here being the angle between, so cosine theta is Q hat dot X hat, the angle between the direction I'm pointing at the next guy and the momentum that's going. So this intuitively makes sense from the point of view that like if I send a particle in a given direction, then it should like land on a point that's pointing that way. So, I mean, obviously that's not obvious when you're not going to infinity. So like you can have some impact parameter and then you're not going to be aligned with like the direction in which your momentum is going. Like, but when you go to very large distances, you have that. So maybe perhaps surprising thing is you think of these plane waves as being like, okay, so you're not looking at the wave packet version of it, like not like localized in space, and then somehow I'm localizing in the celestial sphere. So maybe that's a little bit unintuitive, but the point of view of like, where is my radiation coming from? What momentum does it have to hit me if I'm very far away? Basically aligned with that source. So from that point of view, basically now I've taken this mode expansion and I've taken this large R limit. And basically what that does for me is that gets rid of some of the angular integrals here. So I have my D3K, and so this is right, the energy, and then K squared, yeah, K. And this guy is going away, it's localizing for me. So now I have a way of connecting the position space direction. So I wanted this operator in space-time, local operator in space-time of X with basically these A's now of X hat. So there's some energy scale here. So now let's look at what it actually looks like. So we have the following. Okay, so what does that do for my one that I wrote down here? So I have this limit is R goes to infinity of 1 over R H hat Z Z, and that's negative I kappa over 2 pi squared, some factors of 1 plus EZ bar. This is just coming from all of like the polarization tensors appearing there in completeness relations for this round sphere. And this all multiplies what's only now a Fourier integral left. Okay. So what I have right now is basically by taking large R, I've localized on the celestial sphere, but I still have the ability to basically Fourier transform along U. So if I wanted to select out a given frequency mode, I'd basically have to Fourier transform back in the U variable, and I can do that. So essentially what I'm saying right now is that from the point of view of these free wave packets, I can take my local operator, like, so the question, of course, like when you have quantum theory of gravity, I'm still treating this perturbatively, so I have this like metric operator, but I can basically take a smearing of that integral of that operator along the U coordinate with some frequency. So I'm basically Fourier transforming back to select out the single particle state. So basically I can create that out state by integrating my operator along a point on this future null infinity. So that's good. So what I want to say that we've done here. So right now what we've done is we've connected position and momentum space. Okay, and so this is important from the point of view of, okay, so in momentum space for mass scattering, it's kind of natural that you would think that I label my states with some energy and some direction. So I can use a point on the night sky that it's heading towards, and I can use that energy variable to label my state. So I kind of already have a natural celestial sphere living there. And now we've kind of seen how that matches to the notion of the position space celestial sphere, which I can also think of as being the like infinity limit of the light cone that I have here. So if I look at the origin, and I look at its light cone, when I do boosts, I basically stabilize the locus of constant x squared and also the light cone. And so I can think of that that celestial sphere that's living at that light cone at infinity as like being this cross section of null infinity, canonically identified that, and then also canonically identified with the way that I've embedded, say, in position space, my reference direction Q. So that kind of gives you this idea of like how to connect this SL2C invariance that we want to expect from the London space variables to the one that we're looking at in the spacetime and at null infinity. So the point being here now that, okay, so from the point of view of just doing basically like, okay, so let's think of this following as well. So right, normally if I have my metric, which is just negative dt squared plus dx squared plus dy squared plus dz squared, then what I would look at is I would look at isometries of this metric, say. So typically what happens is then when I'm studying these single particle states, I'm looking at irreps of Poincar, which are the isometries of this. So basically whatever variation I'm doing, I want basically, so the lead derivative of eta mu nu along my vector fields to vanish. So this is the isometries. Now, if I wanted to look at conformal isometries, what I do instead, I have my metric like ds squared is dw w bar, and I demand that the lead derivative of my GAB is basically proportional to GAB. So that's more relaxed than this guy. And so these are my conformal isometries. And because we have this, we basically have Lorentz in R 1 comma D being isomorphic to conformal in RD, we can already see how by relaxing basically the condition that we're imposing on this metric, we've gotten more symmetries. So even though in this case this is isometry, I mean, sorry, it's an equivalence between the number of generators on 2 dimensions lower versus 2 dimensions higher. If I were in the same number of dimensions, this is a more relaxed condition, then I get more symmetries. So what I basically want to say is if we wanted to think of like, okay, so say you said, someone's telling me that there's an infinite number of symmetries, how can I get them? You need to really relax this. So somehow we want to be able to relax this and then also find a way where it's natural too. So from the point of view of the conformal symmetries, if we think of the Lorentz modes, Ln is negative omega w, sorry, this is a w to the n plus 1. Let's make sure I don't mess that up. W n plus 1, yep, w, and these guys have these copies of the Witt algebra. So we have no problem in this 2D plane until you add the point at infinity and make this the Riemann sphere, dealing with the local symmetry algebra here. And if anything, in like in CFTs, you learn that you can do a lot with that. Now, once I think of that as how it's embedded in the space-time, the singularities aren't really good because this is a space-time and I'm like actually there. So I can do a, if I take this guy and I say, okay, well, I know how to write down all of my Poincar generators in these coordinates. And I knew that there was now extra symmetries in 2D. Like, wait, so let me do the logic for you. So I say 4D Lorentz equals 2D cone. So why don't I send this from SL2C to like these CKVs? I could try to do that. And so basically, let me start by writing down what Poincar looks like in the coordinates we introduced above. So in terms of the, okay. So in terms of these vector fields, we have the following. So I'm going to write down a vector field that's going to be look more weird than it is. So bear with this. The point is, if you write something simple and funny notation and then write something difficult in that notation, hopefully it becomes less.
Sorry, Sabrina, may I interrupt you?
Oh, please do. Oh my God, please interrupt me because I realized like.
I got lost a little now that what we're trying to do now.
Okay, good. So what I'm trying to do now is I'm writing Poincar in my coordinates UR ZZ bar.
Okay.
And so by doing that, basically I'm kind of showing what goes wrong if I just try to then look at the Lorentz part of it that I said was isomorphic to the CKVs and like take my Y to be a CKV. Like it's not going to be a isometry anymore, of course.
Okay, so what you're writing now is just the action of
It's just, this
Poincar
is like,
in Z you are.
yeah, so like you do
Okay.
like XO, yeah, whatever. So like just your normal Lorentz transformations are going to look a bit funny because I want to parameterize in a way where I can then naturally promote them to the variables that I want. So I write this down. I can write more terms here. So the point here is you see this YZ DZ, and then I have similar terms with F d by du plus corrections here. So normally what would happen is if I say F is either 1 or it's Z plus Z bar over 1 plus ZZ bar, recall that Z is basically just this coordinate for this S2. So basically every like X hat that you were seeing, so here. So basically now for a very restricted number of F's and Y's, I have my Poincar generators written in a form that I will magically want to see later on. So but basically what I'm emphasizing is the following. So even if you didn't want to worry about the way that I'm writing it right now, what you would want to do though is you want to take your rotation generator. So you have some like xi d by dj minus xj d by di, and then you're just changing coordinates. So I go from t x y z, so z is not great here, to u r z z bar in the manner that I defined above. So this is simple enough to do. So you do that, and it's going to look a bit messy, but basically what you see is in some sense I am naturally parameterizing everything with a function of z and z bar that up to this metric factor basically is like 1 z bar and z bar. So like don't worry about the 1 over z bar because it's a bit of a projective coordinate thing. And then I have a y that is basically 1 z squared. And similarly with i's in front, so it's complex value. So this can be in C, and then these are real coefficients of it. So basically, I have my 10 generators. I have them in this coordinate system, and essentially I'm seeing the local part of, like, basically all I'm saying is that the coordinates, bunny coordinates with the Z projective coordinate matches onto what I would expect to say, like, is my conformal generator. So if my L right now, my L 0, -1, and 1 basically would map onto this Y transformation. So I have my YZ d by dz being basically what I would have before my L -1. So with that in mind, basically one could try to see what would happen if I took my Poincar generators and then did the promotion for the local transformations on this 2-plane that I embedded in my spacetime. So right, I do have this light cone where I've taken my reference direction QMU and embedded it on it. And I know that I want to basically do W to the n+1 dW here. If I did that, then I actually do find that on the light cone, I preserve the metric on the light cone, but basically I shift the metric off the light cone. So if I take a lead derivative of my flat metric with a y that's generally c cubed v, I basically change it as follows: c cubed y z squared plus c cubed. So what I'm emphasizing right now is that basically, right, if I'm on actually the light cone equals 0, so there's a natural sense in which Lorentz transformations are preserving that light cone. So the celestial sphere is kind of the sphere that is that, like, u equals 0 cross section from the point of view of what I'm doing with these Lorentz transformations. If I do that and on u equals 0, I am fine. So that's where, like, the statement of embedding this 2D guy into light cone in the embedding space and then finding the symmetries of that, and you find all of these local CQVs, you would still see that, but you wouldn't know, you no longer have a symmetry for the Minkowski's metric outside of that light cone. But what I want to emphasize now is that basically we need to find a way to think about how we would maybe include it in these symmetries. So that's from the point of view of saying that I told you that I'm saying that I'm taking S matrix elements and mapping them to CFT, and that kinematics let me do it for the global symmetries. And that, like, why would I do it? Well, maybe because I had an infinite number of symmetries. So, like, okay, so the motivation is the following. It's like, so, like, why would I want to take S matrix elements to correlators unless there was an advantage? And when you say there's a 2D CFT that describes scattering, that sounds like an advantage because I open up my yellow book and I see all of these symmetries. I want to find them. So even if I wasn't kind of coming from the point of view of knowing that there are asymptotic symmetries, I kind of want to find a way to look for them. But the point being is that you can also, I guess, naturally like land on these symmetry enhancements from the point of view of a relativist. So from the, okay, so this motivation route was more going from, I know what Lorentz transformations are. I know that there can be enhancements in 2D. Why don't I see them in 4D? And now we're going to go from the relativist point of view, which is I have my asymptotic symmetry group because I have basically this causal structure of the conformal boundary, and I have a class of metrics. What are the symmetries of it? So let's set up that problem. Okay. So say I'm a relativist, and I have, first of all, Minkowski space. Now Minkowski space is relatively boring, because while it's a nice arena for perturbative scattering on top of it, you really want to think of solutions to Einstein's equations that are not trivial. So I'm solving Einstein's equations, and I have vanishing cosmological constant, and I have a stress tensor that's localized. And when I have those conditions, I'm going to call my space-time asymptotically flat. Now, why is that a good name? It's going to turn out that when you're looking at such spacetimes, basically, if you go to infinity, the causal structure of this boundary is going to match what we had for Minkowski space. So the notion of asymptotic flat literally can be taken to be I go very far away, and the asymptotia of my spacetime match the flat spacetime. So, and this is somewhat similar in principle to the way that you kind of think of, I guess one could make an analogy to the way that, like, if you have an interacting theory and then you try to, you think of like the initial and final states. I don't want to conflate it with like the IR divergence issues here, but like the fact that when you're very far away, things are basically free. It's a similar sense in which now when I go very far away, the structure of the space-time matches the flat case. So these are like statements about the asymptotic states kind of in both situations. In and out states in one case, and this case, the data at the conformal boundary. So that's one other kind of theme I want to emphasize. So say I'm doing this. So my problem is, like, my, I guess, task is solve Einstein's equations with vanishing cosmological constant and localized stress tensor. So if I want to do that, so I first need to pick a coordinate system. And so Bondi, Vandenberg, Metzner, and Sachs did this for me. They basically went to Bondi gauge. And if the vector fields that I wrote out were complicated, the gauge itself is not going to look very pretty. I'll write down a first line of it, so to kind of get you familiar with it. So it's not that bad. Basically, the first line here is what the flat metric that you're used to looks like in the coordinates that I was writing out. C bar, okay. And then I have corrections to it. So these corrections are, I guess, the important part. So I'll go through it a little bit more in detail. All right, okay, good. And then there's more corrections here, including an NZ DU/DZ term, which I just want to write out because the point of it is that this guy is going to be also part of this, the free data. Wait, so the gauge is the following. So basically, if I say the U and DZ and DZ bar all equals 0, so I'm just moving along R. So moving along R, you're going to have basically ds squared equals 0. So essentially what I'm saying right now is, like, the coordinate choice that you use is somehow designed so that this radial expansion is going to be good. You can also do the same exercise in harmonic gauge. So basically what I'm doing right now is I fix the gauge, and then once I fix the gauge, basically I can kind of associate some intuition or meaning to the coordinates. But obviously the way that one would do that is, like, whatever you have your gauge, and then you would look at, like, how geodesics behave in that gauge choice, and then basically try to understand what observables would be kind of working back. So we have the advantage of hindsight and years of work of people doing this to be familiar with what these things are. So the first thing we have at our disposal is this flat part. So we already know that basically if all of these corrections are subleading to that, that's the sense in which it's asymptotically flat. And then what you actually do is you just take this metric ansatz, you let out all of these guys. So the way this is solved for is it's already a little bit of work has been done for us. Basically you pick a gauge, you then have each of the components of the metric in that gauge be free functions of the coordinates that you're using, and then you're literally trying to solve Einstein's equations. So you go about doing that, and then what you find here is that the data that's basically freely specifiable are going to be these CZZ terms here. So du of CZZ is often called the News tensor. And this can be freely specified as a function of U, Z, and Z bar. In the same way that on my Cauchy slice at a given fixed time, I would want to specify the independent degrees of freedom. And then, so the point of view here is like I would specify this function of u, and then d by du would be basically the time derivative off that size. So this is my new tensor. These quantities mb and nz basically would capture if I had a boosted mass configuration, then it's going to give a non-zero bonding mass, and the angular momentum aspect captures the spin far away. So from the point of view of playing around with this, one can literally think of, I guess, superimposing the asymptotic perturbations to the metric, and you would see that this is naturally the mass term and this is the angular momentum aspect. And one should point out that in the same way that if you take a point charge and you boost it, there's going to be an angle dependence to the radiative fields. You're going to see that the bonding mass similarly can get an angle dependence. And so this guy is really a function of z and z bar, in the same manner that the Coulomb field can be a function of z and z bar if you have a bunch of moving particles. So we're not just doing electrostatics in the restaurant. Okay, so what I have is the following. I have now my solution. And what I also have basically is that this is supposed to have some localized stress tensor. So I need some fall offs. So I have my T mu nu. So say TUU falls off like 1 over r squared, etc. So I need to specify how TAB behaves at large r. And I'm doing all this analysis near functional infinity. So again, functional infinity is actually a null surface. So the null normal here is n mu, d mu is du is 1 over 2 dr. And so this, one should be able to plug this into the metric and verify that in the flat metric it's null. So I showed corrections here. And then what I want to do normally is, okay, so I have a gauge system, it's a diff invariant. And so when I have such a system, there's going to be constraint equations. So basically, if I look at the equations of motion, the ones that are like dotted into the normal of my Cauchy slice, I need to impose those as constraints to consistently evolve off that Cauchy slice. So what I have is the following set of constraints: du mb is 1 over 4 dz squared and zz dz bar squared z bar and it's TUU, and du and z is 1/4 dz. Okay, so the point is, the point being the following aspect of it is that essentially I have relations between low energy radiative modes and these parameters that I'm saying are giving me like the mass of the system. So I have these constraint equations, and we're going to see a rule for them later. But for me, like the main thing I want to emphasize right now is that essentially the thing that I want to specify is like, this is the data of my radiative fields, like for the out state versus the in state, is this function of u and zz bar here for this 1 over r part of the metric. And so when we keep in mind that before we had this operator h hat, which is supposed to be the metric perturbation, we can actually directly like evaluate the components of that and relate it to CZZ. So I think above when I wrote HZZ route, I want to literally think of this guy as being, it's semi-classically capturing this metric change here. So now when I say that, like that they should be the same, we know that from the quantum field theory point of view, normally I would take my vacuum, I would talk about the Poincar covariance of any like operator correlation function that I'm building up in 4D. From this point of view though, I want to then try to find symmetries here. So I don't want to think of this as saying that there's a canonical background, which is just this first line, and then that everything's perturbation theory around it, so that I'm using basically the symmetries of this background. I would like to find a way to actually like land on this set of symmetries for these classes spacetime. And so the way that the asymptotic symmetry structure is, or the asymptotic symmetry story is phrased is actually kind of reminiscent of kind of what we're seeing with like the conformal class situation, is that you want basically to take a Lie derivative of your metric along your vector field and basically land within the same class of metrics. So maybe like this guy is invariant or something like that. No, the best notation for it is. So let me say it stays the same. So I have some equivalence class, which is being asymptotically flat. So given that, then I have, I've made a gauge fixing already. but there will still be some residual diffeomorphisms that keep me within this solid to fall off. So what I mean that is if I literally look at how I've written this metric down, I have, okay, so I have this round sphere here, and everything is subleading that's also on this S2. So this radiative data is 1 over R compared to this R squared metric, etc. So basically that hierarchy of fall-offs is the way that I've classified this equivalence class of asymptotically flat metrics. And so anything I'm going to call an asymptotic symmetry is going to stay within that equivalence class. So basically what I'm going to say is my asymptotic symmetry group, I'm going to define it as allowed diffeos, residual diffeos basically, mod trivium. So in the same way that one gets more symmetries by preserving less features, this is how that enhancement is going to happen. So what I wanted to emphasize is that this wasn't something that like that they were looking for extra symmetries. They wanted to be able to start from this class and find Poincaré invariance. So from the point of view of somebody who was saying like, okay, I have this planet sitting in my space-time, like otherwise if it weren't there, I would have Poincaré invariance. Now this planet screwed up that I only have like rotation invariance around it or whatever. So like typically the fact that a typical configuration here won't just not have like Poincaré, it won't have any isometries. It would be kind of silly if there was a framework that kind of missed out on the fact that would have had Poincaré invariance if you didn't have that. Like always kind of talking about physics in backgrounds where like even when we deal with like high school billiards experiments, we're implicitly assuming like I guess some lack of interaction between subsystems, right? So like when you have a collision of cars and you want to say momentum conservation is at play there, like we're not using total momentum conservation, we're using momentum conservation for that isolated system. So in this sense here, the isolation is coming at the different directions of the night sky. So essentially what we're going to find is that we're going to have basically a promotion of the Poincaré-like symmetries that we would have normally as global symmetries to each direction in the celestial sphere. And maybe the way that one would see that being natural is again this picture of if you really do think of things being infinitely far away when they're so 2 points, if they're finite angle separated at null infinity, are infinitely physically separated, right? And so in some sense the fact that like you can essentially do an independent symmetry transformation of some like large region of space-time around one of those points and have it not kind of care about what's happening anywhere else is maybe the spirit of why you're seeing these asymptotic symmetries. So all we wanted to look for is a way to find Poincaré, and what Bondi, Vanderburg, Metzger, and Sachs, what they realized is that they found infinitely many more. So what they actually found was the following. So in the vector field that I wrote above, basically F goes from essentially like 1 z bar, z bar, all to any function of z and z bar. And these are called supertranslations. And what they did though still, so the one that I was like pushing for though, right, is this y. I want y to be basically z to the n plus 1 d by dz. But they didn't get that yet. So they excluded this based on things being well-defined in the sphere, which is kind of ironic because maybe from the hindsight of this program, like that's the one that we wanted. Okay, so what do you do about that? Okay, so you're puncturing the sphere when you're doing these transformations. So like at the point of infinity is gonna, like this vector field will be divergent there. And that would be a problem if it weren't for the fact that basically when I'm talking about scattering, I think I'm kind of puncturing anyway with the matter fields being there. So especially from the point of view of looking at local symmetry algebras, this becomes less of a concern. I think it's still a valid thing to debate when it comes to whether you want to do finite superrotations or look at superrotations that have transition functions. Like basically I'm literally just doing a gauge transformation. I'm not like adding a step function and then gluing between two super translated guys. So there are questions still related to that topic that one could be bothered about. But from the point of view of looking at a description of your theory and then looking at infinitesimal transformations around it, these guys should naturally be included in the symmetry algebra, and we can write non-trivial currents for it. So at this stage, basically what we've done so far, let's I guess recap a little bit, is we've looked at 4D isometries, roughly 2D conformal isometries, and then 4D asymptotic symmetries. Sorry, SG is better. Okay, so the thing that we're seeing here is basically the global part was included here, And then to include the local part, we basically need to go up to this asymptotic symmetry story. So we have all these symmetries from different things happening around. Right now, everything I've been saying is basically for 4D has been kind of mostly, at least in this ASG story, in position space. But of course, we know how to go to talk about single particle states and like the representations of Poincar and momentum space here. And so what we're going to want to do later is, I guess, redo some of that in a formal basis, but that's for another day. And for now, what we really want to do is understand why these are symmetries of the S matrix. So I think it's relatively obvious that if I have my vacuum state and I have a Poincar invariant theory, then I want to have some U of lambda or U of the translation generators acting in my Hilbert space, and that for this operator to be unitary. So like this relatively standard construction there, like maybe why would I end up seeing in that framework any notion of this ASG? And that's a lovely kind of question that was answered or addressed by Stromander. And that's what we're going to turn to next. So maybe can you guys let me know how I'm with time, or what's our plan for today? So it's just so I get a sense of how far to go.
So the Choshen, his lecture starts at 3:15. So you can go until 3:15. We're gonna just skip the discussion session for this one and just postpone tutorials, just because of the disruption.
Okay, and what time is it there for you guys now? Because I like in my head
It's 3 right now, so you have 15 minutes.
Okay, oh perfect. Yeah, okay, good. 15 minutes. Okay, perfect. Okay. So I thank you guys for bearing with all that. So basically what we've gotten to the end of essentially section 3.1 in the notes. And so that's good because essentially from there on, it's a lot more like I will go through line by line every equation, not all the words, but I'll like go follow it more closely. So it should be good for this reset. So what I'm going to do with the last 15 minutes, I guess, is just write down for you, I guess the starting point of where we're going to start next time. So let me highlight, I guess, the steps that we're going to follow in the coming lecture. So we're going to first look at soft theorems. And then we're going to end up using our constraint equations to show that basically the canonical charges Q for my asymptotic symmetries give me ward identities that are validated through soft theorems. So basically there's going to be this feedback here between that. And so let me write down the form of this charge so you can see maybe why that isn't quite obvious, and then you see like the steps that you need, etc. So basically, if I went through the canonical formalism and I have this diffeomorphism, I can look at two variations of the metric around a solution, plug in one of those variations being a diffeomorphism, then I get this charge that's supported on, so if my Cauchy slice, my charge would be codimension 2, so it'd be sitting at the boundary of the Cauchy slice. So if I think of null infinity, then basically my charge is going to be supported near spatial infinity. And so I'm going to also need to introduce the antipodal matching condition. So that's on the list for next time. And what I'm going to have here is that basically my charge is going to look as follows. So I have the following 1/8 pi g integral of 2mb ya plus ya and a. Okay, so the kind of integration constants or variables that I only need to set the initial value to define the spacetime are appearing here. So what I'm going to be doing next time is I'm going to be starting from this expression for the charge, where now we know what these MB and A are. We know what the F and the Y are from the symmetries. And so we also have constraint equations. We're going to basically be plugging in ingredients that we've talked about before with the new ingredient of soft theorem so that we know how to evaluate essentially the expectation value of the linear terms of the metric here that are going to be appearing. So that should be fine. The main thing that I want to point out, I guess, for the sake of like making sure that I checked all the boxes of things I wanted to introduce, is that essentially what's going to happen here is that we're going to see the following thing. So we're going to see that basically there are this 4D ASG is equivalent to soft theorems in QFT, and further is equivalent to a 2D current. So my whole emphasis on like talking about CKVs for no reason ahead of time is because basically there is this triality of connections. This is the first one that this is the kind of the thing where a lot of people working on it out of Harvard for a while, where we were basically for every soft theorem, or even like Cachazo and Strominger found a new soft theorem, finding a corresponding asymptotic symmetry interpretation. But the real like teaser for that is that it looks like 2D currents. So in particular, this YA that we're talking about here, and how by going to this asymptotic symmetry story, we can get these conformal generators. That's going to be central to motivating this change of basis. So ideally, next time, what I'm going to be getting through is hopefully nice and slow through 3. And then after that, we get to go straight into different aspects of celestial amplitudes. And recall that basically we need, we only need global conformal invariance, which is Lorentz invariance, to trivially have these celestial amplitudes. Like by definition, right, I want this object that transforms like a correlator starting from an in state. And I can do that just from the rep theory, because this is just a different representation, which I'll set up also in the lecture after next, hopefully. But the key of why we're doing it, and it's why we're spending so much time on the soft theorem side of stories, is that basically we now have currents here. And so that feature is important because otherwise you would basically just be doing an exercise and changing between representations. So hopefully, I know we had a bit of a funny like lead